Thank you for joining this lesson. We're going to discuss physics paper 1 in preparation for the Kcse and also in preparation for the exams to come in future. So let's be following keenly so that you people may benefit at the end of it. Make sure you are subscribed. Make sure you share with a friend. Invite someone to this live broadcast. You can just share the link. Ensure you are a subscribed member of Shifting Grades online school. Yeah, so our NAPA is on the screen for those who would like to consult in future. So please ensure that you reach out to us using the number displayed on the screen. So we're going to go through a physics paper 1, a total of 80 marks. We'll be giving even guidelines on how to answer a few questions. And in case you are stuck somewhere when you are handling mathematics or physics, the number to consult is still on the screen. Number 1, distinguish between mass and weight of a body. I want to make something clear even before I go to answering of this question. When you are told to distinguish, it's very different from differentiate. When I tell you to differentiate between mass and weight, you can give any difference between the two, either basing your argument on the measuring instrument, the measuring unit, whether one is a vector, the other one is a scalar, such differences. But when we are talking about distinguishing, then we go directly to the definitions of the two terms which have been involved. Distinguish between mass and weight. Mass is the quantity of matter in a substance. You give the definition. Mass is the quantity of matter. The quantity of matter in a substance. While, sorry, I didn't check that line well, but we say that while weight is the measure of the pull of gravity in an object or in a body. So when I say distinguish, then I expect the difference based on the specific definitions of the two. Number 2, a density bottle full of water weighs 45 grams. When full of mercury of relative density 13.6, it weighs 360 grams. Calculate the weight of the empty density bottle. What we're supposed to know here is that, okay, this is measurement 1. Actually, this is work for Form 1. I think it's good it's also Form 1. We're discussing paper 1 and it's good we classify all these topics. Remember, physics paper 1 cuts across all the way from Form 1 to Form 4, and we'll be classifying all these topics. A density bottle is already measuring this mass when it is full of water. Then we have another mass of 360 when full of mercury. So the first thing that we're supposed to understand is that a mass of the empty density bottle is not given, and that is something we can calculate. So we say let the mass of the density bottle, which is empty now, to be x. If it's x, then we can say mass of water mass of water will be equal to 45 minus x. These are grams. Yeah, 45 minus x. Because when the density bottle is having water, it weighs 45. And when empty, it's weighing x. Then the mass of water will be that one. Now, we can also get mass of what we are calling a mass of mercury. So let me get mass of mercury. So mass of mercury. Mass of mercury. Yeah, Hg. Let me write it in the scientific abbreviation, scientific formula. Mass of mercury is going to be also, when we take 360 and we subtract x, again in grams. There is something very sensitive that I would like to outline. In the cover page of this paper, we are told you may use the following constants where necessary. The value of G is 10 and the density of water is 1,000. 1,000 can also be expressed as 1 gram per cubic centimeter. So that one has to be understood also. Sometimes the instructions, though in rare occasions, might be given on the cover page. Now it is upon you to apply them where necessary. Where necessary includes number 2. So now, if we are using this now in number 2, then we can say we can now get volumes. Let's talk about volumes. And generally, we should be knowing that because density is given by mass over volume, then volume will be given by mass out of density. Yeah, mass out of density. So with this, we can get volume of water. Volume of water is going to be mass out of density. Mass, which is equivalent to 45 minus x, divided by 1, and this will just become volume in cubic centimeters, because we have divided the value by the density, which is just 1. Yeah, by the density, which is just 1. So with that, we can also say that volume of mercury, which will be the same as volume of, it's also the same as the volume of the density bottle, is going to be 45 minus x. Remember, this volume of water is the one filling the density bottle, and we have known the volume of water, which means the volume of the mercury, which will fill the same density bottle, and the volume of the density bottle itself are all equal to the volume of water, because the water had filled the density bottle and mercury is filling the same density bottle. So people have to understand that calculation. Allow me now, because we have volume, allow me now express volume. Density, I have to mention something about relative density, though we'll be talking about it more during floating and sinking. Yeah, we will talk about it more during floating and sinking. It is usually the density of a substance with respect to the density of water. With respect to the density of water. I hope you people are getting me clearly from wherever you are. I hope you guys are getting me well. Okay. If this is the density with respect to the density of water, then it means the actual density of mercury then is 13.6 grams per cubic centimeter, because with respect to the density of water, we're getting 13.6. And at this point now, we can go mathematics way and say, now that volume for the mercury now that a volume, which is 45 minus x, is given by mass over density, then this will be out of mass, which is equivalent to 360 minus x, divide by the volume, mass over volume. For us to get volume with mass over density, so the density is 13.6. Yeah, 13.6. Across multiplication at this point is going to give us a 612 minus 13.6x equals to 360 minus x. Now, when we group like terms together, this will be 12.6x equals to 252. And dividing through by 12.6, the value of x, which we had let to be mass of density bottle, now is becoming 20. This will be 20 grams. Remember, the question is telling us to calculate the weight of density bottle, not the mass. So with this mass, now we can go to weight, whereby weight is given by mg, each in SI units. So 20 has to be divided by 1,000 for it to become kilograms. Then now times 10. This becomes 0.2 newtons. Yeah. Number 3, this is a question on it's a question on forces, again from one work. Needle floats on clean water but sinks when some detergent is added to the water. Explain. It floats on clean water due to surface tension. Now, this is the force which makes the surface of a liquid to behave like a thin, stretched, elastic skin, and it can hold some substances. That is why a needle, when placed carefully on the surface, it shall float. Now we are saying when a detergent is added, it lowers the coercive force. Hence weakening. The surface tension, or simply breaking the surface tension. Hence breaking or weakening the surface tension. Hence breaking the surface tension. Now we can continue. There is number 4. Sorry, there was a network issue, but now we can proceed. Number 4, state 2 reasons why water is unsuitable as a thermometric liquid. Okay, you begin by, first of all, knowing the properties which a thermometric liquid is supposed to possess, and we know them. So we identify the ones that water lacks. For example, water has a narrow range of temperature. Water has a narrow range of temperature. That means at 0 degrees Celsius, it freezes. Then at 100, it vaporizes. Only 100. A thermometric liquid is supposed to have a wide range of temperature, a very wide range of temperature. Okay, a good thermometric liquid, while it is inside the glass tube, no, it's supposed to be visible, supposed to be transparent. No, it's supposed to be opaque, but water is clear. So water is not visible. Water is not visible due to it's not clearly visible. Can just use that word because anyway you can view it, but it is not clearly visible, and this is making it unsuitable because you may not make very precise observations. It also does not contract and expand uniformly. Does not contract and expand uniformly. We usually say that a good thermometric liquid is supposed to expand and contract uniformly, and many more, because a good thermometric liquid is not supposed to weight the glass, but water weights the glass due to its weak cohesion. So there are many properties, and you're supposed to be able to highlight them. That's again from one work. Number 5, state out the density of water change as the temperature is lowered, say from 15 degrees to freezing point. Freezing point is a 0 degrees Celsius, so you must be knowing that point. We usually know that there is what we call the anomalous expansion of water. The anomalous expansion of water, which happen between 0 and 4 degrees. So we say that from 15 to 4, once you are lowering temperature, you are also lowering volume. That means you are increasing density. It's good I write that density is given by mass over volume. So when you are lowering temperature, you are reducing volume and thus increasing density. That would be very normal for water between 15 as you lower the temperature all the way to 4. But between 4 and the freezing point, now things change. Water behaves abnormally at that point. So you say from 15 degrees Celsius to 4 degrees Celsius, decrease in temperature leads to an increase in the density of water. Then now from 4 degrees Celsius to 0 degrees Celsius, the density, it is a decrease in temperature, yes, but instead of density continuing to increase, the density now decreases. This is the anomalous expansion. This is the anomalous expansion of water, the unusual behavior of water, whereby instead of contracting between 0 and 4, it will now expand at that particular point. Explain how a vacuum flask is able to minimize heat loss by radiation. So the vacuum reduces, the vacuum flask or the vacuum minimizes the vacuum flask minimizes radiation by having silvery walls, silvery inner walls. Yeah, we call them silvery inner walls. So the inner walls, when they are highly polished or simply silvery, they are going to absorb very little heat from the liquid which has been stored inside. They will absorb very little because highly polished surfaces are poor absorbers of heat. Therefore, the heat will not be absorbed by the walls which are storing the content of the flask. So you must know that. Another question in number 7. How is the boiling point of water affected by addition of salt to the water? It's good to know that impurities increase boiling point. If it was about a melting substance, then we would have said impurities lower melting. Therefore, the boiling point of water is increased. The boiling point of water is increased. It is increased. So if pure water boils at exactly 100 degrees due to addition of impurities, then water is going to boil at a temperature slightly above the ordinary boiling point. State 2 practical applications of the principle of transmission of pressure in fluids. We call it the Pascal's principle. Pascal's principle. It's good for people to know an alternative name. Pascal's principle. The Pascal's principle. There are some machinery which work under this principle. One is the hydraulic lift and also the hydraulic press. We also have hydraulic brake system. The hydraulic brake system. Yeah, the hydraulic brake system. It also applies the same principle. Number 9, which is on this actually Form 2. This is Form 2. We're talking about applications of the transmission of pressure. That's Form 1. Then up there about a boiling point of water. Okay, this one will be Form 3. I know in chemistry it is even Form 1. I know in chemistry about impurities and boiling points, that is Form 1, but in physics you will study it on quantity of heat. This is Form 1, heat transfer. Density bottle, density of water changes. This one is going to be Form 1. That's Form 1 work. Yeah, we will categorize all the questions. Now we are dealing with Form 2. As we continue learning, let people know that we have our programs here for the holiday. Students who are in secondary schools, kindly enroll to this. You are really going to benefit. Register through the number which is on the screen, 0704 15 33 66. For physics and mathematics, use the number 0704 15 33 66. When you consult about the programs using that number, I'll be here to assist you and give you the way forward. Now, number 9 is a Form 2 question, the turning effect of a force. A uniform rod, 1 meter long, weighing 50, is suspended or is supported horizontally on two knife edges. A and B, placed 10 centimeters from its ends. Calculate the reaction at support A when 100 weight is suspended 10 centimeters from the midpoint of the rod towards A for 3 centimeters. This is the turning effect of a force. Form 2 topic, I think topic 3. A very sensitive topic which is applied widely. It's even a practical topic. Yeah, it is even a practical topic. Okay, so we are talking of 10 centimeters from the ends. We have a knife edge. So there is a knife edge here. We're calling it A. Then there is another knife edge, 10 centimeters from the other end. We call it knife edge B. These are 10 centimeters. These are 10 centimeters from the ends. That's how they are. Then we are told that it weighs 50 newtons, which means at the exact center, at the 50 centimeter mark, there is a 50 Newton weight acting downwards. The weight of the instrument itself, the weight of the horizontal metal rod itself. The weight of any material acts downwards through its geometrical center if it is uniform. So for our case, it is uniform. Then now what are we saying next there? We are told that calculate the reaction at A when 100 is suspended 10 centimeters from the midpoint. The midpoint is 50. So 10 centimeters away, it means 10 centimeters somewhere here. There is 100 Newton downwards acting there. So we're supposed to know that with this, we now can talk about downward moments and upward, not moments, downward forces and upward forces. Remember, for a system in equilibrium, all downward forces should equal all the upward forces. All downward forces should equal all the upward forces. So we are supposed to know that upward forces are equivalent to upward forces. Okay, downward, let's take downwards. Downward forces are going to be 150, giving us 150 newtons, sorry, 150 newtons. Now, the upward forces are going to be the respective reactions at A and also at B. So we can take moments about point A, and we will say that 50 and 100 are going to be clockwise. So 100 newtons multiplied by, from where 100 is acting, it is 10 centimeters from the center, from the middle. And also, the point A itself is 10 centimeters from origin, which means now the 50 centimeters up to the center has been narrowed down, 10 and 10, remaining with only 30, which can be converted to 0.3 meters. Plus, for 50, we will have 50, and with reference to point A, then we will have 0.3 0.4 meters because it is 40 centimeters. Now we convert it because 50 newtons is at the 50 centimeter mark, but the turning point is the turning point is point A. Now we should equate this to the reaction at B, because reaction now at B becomes our only clockwise moment. Reaction at B is our clockwise moment. So the reaction at B is acting 80 centimeters away. So it will be the reaction at B multiplied by the distance there from point A to where B is just 0.8. And this will give us the force at B being equal to 62.5 Newton. Once you get that reaction, now you will say that total upward forces should be equal to the total downward forces. So the reaction at A plus the reaction at B should give us the total downward forces, because those two reactions are the upward forces. Now they should give us the downward forces. And this is going to exactly be 87.5 Newton. 87.5 newtons. Number 10, state two ways in which a lab Bunsen burner is able to keep its stable state of equilibrium. The stable state of equilibrium. This one is by having a wide base or a broad base. There is the broad base, wide base, which increases the tilting angle, which increase the angle of tilt before toppling up. Before toppling. So if you displace a Bunsen burner, there is a very big angle which has been increased by the wide base. So before toppling over, it should go through a very big angle of tilt, which might make it very difficult for it to be unstable. Then there is also the heavy base. The heavy base, which lowers the position of the center of gravity of the whole substance, of the whole apparatus. And you know, the lower the position of COG now, then the more stable an object is going to be. So those are the two factors which ensure that a Bunsen burner is really stable. Number 11, the graph below represents relationship between extension in centimeters and weight in newtons suspended on a spring. So we have the graph here. Extension is in centimeters, and we are also talking about the weight in newtons. The question that we've been asked to do is to determine the spring constant of the spring. Spring constant of the spring. It's good for people to know that force is directly proportional to extension. So force equals to spring constant multiplied by E. That means in case we plot force on the y-axis and extension on the x-axis, the graph is going to pass through the origin because it is not having, the equation is not having the y-intercept. And spring constant becomes the K. In this case, K becomes spring constant, which is in this case our slope. because it multiplies the quantity on the x-axis. But now we have interchanged. So let's interchange this equation and say that extension equals to force divided by the spring constant. Remember, now extension is the one on the y-axis and force is on the x-axis, which means the coefficient of force will give us slope. So from this interpretation, when we interpret now this equation, we will say that we have E on the y-axis and we are having 1 over k then multiplied by f, and f is in the x, which means the slope is going to be the coefficient of f, which is 1 out of k. So we need now to find the value of the slope, then it shall be equated to 1 over k. Students must know that you're not supposed to memorize quantities in physics and how things are done. Interpret every question as a new question, because a student who is used to force against extension will end up doing a big mess in this question, because they will just find the spring constant and they will think they will get the extension and they will think they are done. Now we are supposed to get 2 points which are lying on the 2 points which are lying on the line. So we can get the coordinates here, because we need change in y over change in x. Change in y over change in x. So that means we need to start from coordinate. The coordinate here near B, the coordinate there is going to be 2.3. Yeah. 2.3, 12. And the other one here, down here, we have a 0.8, 4. So we have picked 2 coordinates which are lying on the line. For us to get the slope, we need to take change in y over change in x. So 12 minus 4 divided by 2.3 minus 0.8. So this is going to be 8 out of 2.3 minus 0.8, giving us 1.5. 1.5. So this slope is going to be 5.33. 5.33. 5.33. Remember, this one is a centimeters per Newton. Centimeters per Newton, which means our K now, because 1 over K equals to 5.333. Then K is going to be, using your calculator, you find the reciprocal also. The reciprocal of this, which is going to be when we take the reciprocal, we get 0.1875. And these are newtons per centimeter. If these are the newtons in a centimeter, then it means per meter. We can also put it in SI units. If that is per centimeter, then per meter, you multiply by 100. This is going to be 18.75 newtons per meter. This is going to be the extension. No, not the extension, sorry. The spring constant. The spring constant. Yeah, that is its value. Then now we have more questions about the same. If 2 such identical springs are arranged in series and support a load of 2.5 Newton. Determine the total extension of the system. When springs are arranged in series, we can use two approaches. We can say the extension of one is going to multiply by the number of springs, or the spring constant of one is going to divide by the number of springs there. I don't know whether you've understood me, but we can approach using those two methods. So let's work out the two alternatives. One, I'm saying this, we need to use 2.5 and one spring. You know, extension is usually given by force out of K. So I need to take 2.5 divide by, okay, we can get it in centimeters to reduce very small numbers, to stop working with very small numbers. So we can divide by 0.1875. What extension are we going to get here? This is 13.33. Yeah, 13.33 centimeters. And this is one spring. So for two springs now, the extension doubles because they are now 2. So we just multiply by 2. And this gives us, okay, this is going to give us a 26.67, because it will be 666.67 centimeters. Now, alternatively, this is what we are talking about, an alternative approach. An alternative approach says that in case we have the spring constant being this, then the spring constant of two springs, for two springs, the spring constant will divide by 2. So for two springs, spring constant is going to be, it divides by 2 now. It divides by 2. So we need to take 18.75 over 2, giving us 9.375 newtons per meter. Then, if the general spring constant will be this, what about the extension, which is given by force out of now the spring constant? So 2.5 out of 9.375. So 2.5 divided by this value is giving us 0.26666 recurring, and these are going to be meters, which is the equivalence of the centimeters we had gotten, 26.67 centimeters. So that is the total extension when two springs are connected in series. Number 12. A stone of mass 2 kg is released from a height. It's released from a height of 45 meters from the ground. Determine the momentum of the stone as it strikes the ground. Determine the momentum of the stone as it strikes the ground. I want to believe that you people are still following with the lesson. Yeah. So we told to determine method to determine. I'm still looking at your comments. Thank you so much. Thank you so much for being very, for being very cooperative in the lessons. Remember, our consultation line remains 0704 15 33 66. 0704 15 33 66. A stone of mass 2 is being released now from a ground. This is a Form 3 topic. Yeah, it's a Form 3 topic. And we'll be talking about change in energy. When an object is released from up there, it is usually possessing what we call a gravitational potential energy up there. But as it comes down, because it will be losing the height now, it will lose the gravitational potential energy and it gains what we call kinetic energy. As it comes down, the speed will be increasing. So as it loses the height, in brackets, the gravitational potential energy, it will be alternatively gaining, or at the same rate, it will be gaining kinetic energy. So we can calculate the mass with which, the speed with which it shall land on the ground with. So we will talk of gravitational potential energy the body is going to lose will be equal to the kinetic energy the body shall gain. Yeah, it is equal to the kinetic energy that the body will gain. So we can say gravitational potential energy is given by mass times g times h. This is equal to half kinetic energy now, mv squared. Yeah, half mv squared. And at this point, remember, we can even, because the mass is of the same object, we don't have to substitute the same value. So it can even cancel at that point. And we say 10 times g is 10 times the height of 45 equals to half times a known velocity squared. So this velocity squared shall be, you multiply through by 2 and you get 900 equals to v squared. So that the value of v now becomes the square root, which is 30 meters per second. Yeah, 30 meters per second. Now with the velocity, we can say that momentum is given by mass times velocity. So a mass of 2 kg and a velocity of 30, this is going to give us exactly 60. Now this is momentum. There are several units of momentum, but let's use the derived units. From the quantities that we are multiplying, mass is in kilograms, speed is in meters per second. So kilogram meter per second. We call it a derived unit. Kilogram meter per second. The kilogram meter per second. Section B, 55 marks. In the last 48 minutes, we have now covered only 25 minutes. I doubt whether we will go. I don't know whether it's practically possible. We go for the 55 marks or we set a day for section 2. Nevertheless, I'm going to handle the first question in this section. Then we will see what to do. State Newton's first law of motion. This is also called the law of inertia. It's also called the law of inertia. We say that generally objects have a tendency of refusing change, including human beings. So we say that a body remains in its state of rest. A body remains in its state of motion, in its state of rest. So we begin with the rest. Then we go to motion in state of rest, or motion, uniform motion in a straight line, unless acted upon by an external force. Unless acted upon by an external force, a body remains in its state of rest or motion in a straight line, and actually uniform motion in a straight line, unless acted upon by an external force. So if you have a body which is resting, that body will remain at rest. That body will remain at rest. If a body is moving uniformly on a straight line, it will remain moving unless acted upon external force. Number 2, what is the relation between force and momentum? We usually say that, okay, you know that we know that according to the second law of motion now, let me begin mathematically, then I give the statement that shows the relation. Mathematically, we see that the external force which can cause acceleration is usually directly proportional to the rate of change of momentum. Rate of change of momentum means mv minus mu. This is a final momentum minus initial momentum, the rate of change in momentum. Then there is what we call force now. There's what you call force. So this mathematical statement can now be said that force is equal to the rate of change in momentum, or change of momentum. The rate of change of momentum. The rate of change of momentum. Remember, there is another quantity called impulse. You know, impulse is on a different note now. Impulse is given by Ft, which means when you cross multiply the above equation by T, you'll have Ft being equal to mv minus mu. And for this case, we will say impulse equals to change in momentum. Impulse equals to change in momentum. So the difference in force and impulse is that force is rate of change in momentum, but impulse is just change, not rate, just change. This one was not part of the question. I was just reminding you something in Form 3 physics. Now, part B is a calculation which is advising us that a minibus of mass 2250 kilogram moving at 90 kilometers per hour collides head-on with a stationary car of mass 1250 kilograms. If the impact takes 4 seconds before the two move together at a common velocity, determine part 1, the common velocity. Determine the common velocity. So we're supposed to know that in all types of collisions, linear momentum is usually preserved, it's conserved. So we say that linear momentum before collision, linear momentum is equal to linear momentum before equals to linear momentum after collision. linear momentum after collision. It's usually conserved. How do we get linear momentum? Generally, momentum is given by mass times velocity. Something we're supposed to know is that we should work with SI units. So the 90 kilometer per meter, kilometer per hour, should be converted to meters per second. Should be converted to meters per second. And so we're supposed to say that the 90 kilometers per hour have to be converted by multiplying the kilometers by 1,000 and the hours by 36,000, 3600. So that we convert. So this is going to give us what? Exactly 20. Exactly 20. 25. Let me confirm 90 by 100. Then we divide by that 600. This will be 25, not 20. 25 meters per second. So 25 meters per second. So now with velocity, we can say that linear momentum before collision, it was this minibus 2250 multiplied by 25 plus the car 1250. It was stationary, so times a velocity of 0. This will be the same as they combine 2250 plus 1250 times the common velocity, which is unknown. So we can talk of the common velocity. So 3500 by V equals to, when the other side is computed, it will be 56,250. This way. So to remain with V, you divide through, and this will give us exactly 16.07 meters per second. Meters per second. So that is the common velocity. Then impulse of the bus. We're supposed to know that impulse is given by, actually it's something we had talked about up there. Impulse by definition now will be given by change in momentum, not the rate of change in momentum of the bus, of the minibus, because we are talking about the minibus in this case, of the minibus. Change in momentum of the minibus. Change in momentum of the minibus. So impulse is going to be, for the minibus, it was initially moving at 2250 by 25. That is initial. Let me start with the final. I think we have to work it that way. We begin with the final minus initial. Final minus initial. Change in momentum will be final momentum 2250 by the speed the minibus is moving at minus initial momentum 2250 by 25. This is going to give us impulse, which is a negative. That is negative 2000. No, 289.3. Being impulse and being change in momentum, it will bear the units of momentum, kg meter per second, or 289.3 Newton second. Newton second because impulse is also given by Ft. Impulse is also given by Ft, and the SI unit will be resolved to be Newton second. Newton second. Number 14. Number 14, this is on gas laws. The diagram in the figure below shows an experiment to investigate the relationship between volume and temperature of a fixed mass of a gas at constant pressure. Already, this information can already lead you to the gas law being investigated. And that will simply be Charles. Charles' law is the one that compares volume and temperature when pressure is constant. So we have a thermometer there. Thermometer measures temperature. We have a water bath. We have a stirrer. We have concentrated sulfuric acid bead. Then we have a dry air trapped there. We have some heat. Then there is a scale, which is also attached there. Explain the function of the concentrated sulfuric acid. The functions. There should be some functions. One, it is a drying agent. For the gas. Not gas, you can call it air generally. So the air inside there must be dry air, and the sulfuric acid bead fixed there is acting, one, as a drying agent. Two, it is a pointer. It is a pointer for the level of air in the glass tube. Yeah, in the glass tube. So in such a glass tube, we will be following the level of the concentrated sulfuric acid for us to know how the dry air is expanding or contracting. So to monitor the length of air column, we follow the mark by the concentrated sulfuric acid. So those are the two functions, the two main functions of the concentrated sulfuric acid. So the two main functions of the concentrated sulfuric acid. Roman 2 states measurements to be taken in the above experiments. So you just guided by the apparatus provided. One of the apparatus is thermometer. And we've said from the look of things, we are doing. So apart from the apparatus, what is necessary? What should be compared when verifying the Charles law? So we'll talk of from the thermometer, we measure temperature. Temperature from the thermometer that you can see. Then the other thing to be measured is the height. The heights or simply the lengths of the air columns. Of the air column. You know, the air column is the one now to represent volume of air. So when the column is small, volume has decreased. When the column is high, volume has increased. So those are the two basic measurements in such an experiment. State the law being investigated in the experiment above. So the law itself is the Charles law. We have already mentioned it is the Charles law, but this is not a statement of the law. Charles law, we have just mentioned it. So to state it, it states that the volume of a fixed mass of a gas states that the volume of a fixed mass of a gas is directly proportional to the absolute temperature of the gas. To the absolute temperature of the gas at constant pressure. At constant pressure. Very key. At constant pressure. It's a very key statement. So at this point, I must advise students to ensure that they are talking about absolute temperature, because when you just say temperature, you're going to be wrong. You're seriously going to be wrong. You'll be penalized, and that is not good. So we're supposed to safeguard our marks by ensuring that we deliver what is required in the papers by the examiners. Then also you give the last condition at a constant pressure. That one has to be there. At a constant pressure. That one is supposed to be there. Roman 4, name 2 physical properties to be kept constant in this experiment. When verifying the Charles law, there are some quantities which are supposed to be constant, and they are already in the law. We have already mentioned them. We are talking of states that the volume of a fixed mass of a gas, fixed mass. So mass has to remain constant. Then another quantity is pressure at a constant pressure. So pressure and mass are usually constant in the verification of the Charles law. In the verification of the Charles law, pressure has to be constant. On the grid shown in the figure below, sketch a graph of volume against temperature, which is in degrees Celsius, for the experiment above. Clearly, mark with letter T the absolute zero temperature. Absolute zero temperature. So whenever we are working out this, we're supposed to know that, okay, at the point here, this is negative 250. So negative 273 will be somewhere here. Beyond 250 and approaching 300 negative. So that is where T is going to be. And now I'm supposed to do the graph. Because they are directly proportional, it's going to be a straight line. But now beyond this, I'm going to use dotted. Yeah. So the absolute temperature is there, which is a negative 273 degrees Celsius. So this graph will also be evaluated, but using the Kelvin scale, whereby you'll be given the axis like this. Then you are told this is temperature in Kelvin. This is volume in cubic centimeters. Then you draw the graph. Now, in such a case, you ensure that you pass through the origin. In such a case, you pass through the origin. You're passing through the origin because that is now the zero absolute, the absolute zero temperature, which is equivalent to negative 273 degrees Celsius. So it's just the same graph, only that zero, the absolute zero temperature, for the Celsius scale, it will be represented by negative 273. So please master that. We continue. Use kinetic theory of gases to explain the law that we have mentioned, the Charles law. So the Charles law stated that temperature and volume are directly proportional. So you say that as the temperature increases, the kinetic energy increases, and hence the velocity of the gas molecules. As the temperature increases, the kinetic energy and hence the velocity. And hence the velocity of the air particles or air molecules also increases. So you find that the temperature is increasing, and also the gas molecules are also increasing. Increases. Hence, increase in volume. Increase in volume. The gas is also talking about a constant pressure. How do we ensure that pressure is kept constant? The increase in volume. The increase in volume leads to, or the increase in volume, yeah, leads to corresponding increase in collisions. Not really. The collisions will not be affected. Let me put it in this way. You know, we are having a pressure which must be constant. And how is it kept constant? How is pressure kept constant? Increase in temperature, there is a corresponding increase in volume, thus not affecting the pressure. So the number of collisions per unit time, the number of collisions of the particles of air, the number of collisions of the particles of air with the walls of the container, the walls of the container per unit time remains constant. Remains constant. Why is it remaining constant? Because increasing the velocity or increasing vibrations, there is also a corresponding increase in volume. If this was happening in a fixed volume, then we would have had an increase in pressure. So remain constant, hence pressure remaining constant, hence pressure is constant. So that is what keeps the pressure constant. That is what keeps the pressure constant. That is what keeps the pressure constant. Remember to subscribe. Remember to share. Remember to invite friends to the live broadcast. We continue handling the paper. The figure below shows the cross-section of a wheel and axle of radius 6.5 and 1.5 centimeters respectively, used to lift a load. Use it to answer the questions that follow. We are calculating part 1, the mechanical advantage. Something that you're supposed to know about mechanical advantage. Being a ratio, it has no units, and it is a ratio of load and effort. So a load of 150 and an effort of 50. This will give us exactly 3. We are done. 2, the velocity ratio. Velocity ratio in a wheel and axle is usually given by radius of the bigger wheel out of radius of the axle. Yeah, radius of the axle. Wheel and axle. So the wheel, an axle is usually connected at a point here. So the axle now is having a radius. The wheel is also having a radius. So 6.5 and 1.5 respectively. Is that so? We can confirm 6.5 and 1.5. This will give us 4.333. Being a ratio again, units. Yeah, being a ratio, no units. Thank you guys for following. I can see you are seriously following. Yeah, so thank you so much for following. We can go to efficiency. Efficiency is usually given by mechanical advantage out of velocity ratio times 100. Mechanical advantage out of velocity ratio multiplied by 100. This is now going to give us 69.23. Percentage. So that is the efficiency of the machine. Efficiency of the machine. We can adjust to part B of this. Yeah, adjust to part B, whereby we are told that we define the term elastic potential energy. Elastic potential energy. This is the energy possessed. This is the energy possessed in a stretched spring. In a stretched or compressed spring. It can be any other material anyway, any other elastic material. Once it is stretched, the work done on it. In other words, this is the work done on stretching or compressing materials. The work done in stretching or compressing materials. 30 grams of water are allowed to fall down a balcony. To fall down a balcony. Part 1, calculate the height of the balcony if the water hits the ground with a velocity of 30 meters. So we can use the change in energy. I think this is something we have applied somewhere. The gravitational potential energy lost equals to the kinetic energy attained. That's how we give kinetic energy. This is how we give gravitational potential energy. So the gravitational potential energy, because it is the same body, mass can cancel out. And we will say G times a known height equals to half times V squared. So this means to remain with H, now we have to divide through by G, whereby it will be 30 by 30 out of 2 times 10, which gives us 20. And so we get 45 meters. Yeah, the height is 45 meters when you divide properly. State the energy changes by the water. There is gravitational potential energy, then kinetic energy, then sound as it lands. So there is gravitational potential energy. As it falls, it becomes kinetic energy. But during the landing, some energy will become heat. Some other energy will become sound as the water falls down. So these are the expected energy changes. Now we got number 16 here on linear motion. That is a physics form 3, topic 1 in form 3. A paper tape was attached to a moving trolley and allowed to run through a ticker timer. The figure below shows the section of the tape. So you can see the first 1.5 centimeters, region AB. Then we have the last 3.2 centimeters, and that is the region CD. Yeah, the region CD. The region CD. We have not been given the direction of the pulling of the trolley, but let's see the questions. If the frequency of the tape is 100, determine part 1 velocity at AB. Now, for us to determine velocity, we're supposed to know periodic time first. The time taken for the ticker timer to make a dot and a consecutive dot. That is called periodic time. So periodic time T is given by the reciprocal of F. This will be 1/100, which is going to be 0.01 seconds. 0.01 seconds. So how do we get velocity at AB? The distance within there, which is 1.5, divide by the time taken to cover that distance. So we consider now the number of spaces. So 1, 2, 3, 4, 5. So the time taken will be 5 dots, 5 spaces by 0.01. And this is going to give us exactly 30 centimeters per second, which is 0.3 meters in a second. 0.3 meters in a second. Part 2, velocity at CD. So the velocity at CD is going to be given by, the distance there is 3.2, divided by 0.01 seconds times the number of spaces there. The number of spaces in region CD. I'm only seeing 1, 2, 3. 1, 2, 3. So there are 3 spaces there. 3 spaces. So this will give us a velocity of 106.6666. So we can have 67 centimeters per second, which can be converted to meters. And this will be 1.067 meters per second. Yeah, that will be meters per second. Part 3, acceleration of the trolley. Acceleration of the trolley. We know that generally acceleration is usually given by final velocity, initial velocity out of time. What is the final velocity? 1.067 minus initial velocity 0.3, then divided by time. The time to accelerate now, this is where the deal is. 0.01 times how many spaces do we count? In this case, we count the full spaces between B and C. In this transitioning point, we will have 1, 2, 3, 4, 5, 6, 7. So we are having 7. Then we add. Now within the regions themselves, we take half the dots. For example, we are having at this point 1, 2, 3, 4, 5, and on the other side 1, 2, 3. So 5 and 3, we take the half. So 8 divided by 2, we get 4. So we'll be using 11. We'll be using 11 spaces. 11 spaces. So this is going to give us an 9.7 meters per second squared. 9.7 meters per second squared. So that is how we get acceleration from a ticker timer. Define the term part B, Roman 1, angular velocity. This is the rate of change of angular displacement. Of change of angular displacement. The rate of change of angular displacement. The rate of change of angular displacement. Part C. The figure below shows a spring tied to an object of mass m and made to rotate in a circular path of radius r. You can see the diagram. An object is moving there. That object is having a mass m. Actually, the mass m is here. Then we have a spring balance there. That means the string is held here because the radius is here of that path. Then it's supposed now to be rotated now. State and explain the observation that would be made on the spring balance if the object is whirled faster. Whirled faster means that we are increasing velocity. So the velocity will also increase the centripetal force required. And you know the spring is going to record centripetal force. The strings are going to be stretched. So we say that the strings or the spring extends more. This is due to increase in the speed. Increase in the speed, which leads to increase in the centripetal force required. Therefore, we expect an increase in the extension of the spring constant. Part D. The figure below shows an object of mass 0.5 kg whirled in a vertical circle, very key, at a velocity of 5 meters per second, as shown by a string 0.2 meters long. A string 0.2 meters long. So the string being 0.2 meters long, that means the circular path has a radius of 0.2 meters. Determine the tension in the string when the object is at the position shown. Position shown means the topmost position. So for us to get tension at the topmost, this is usually tension minimum. It's given by centripetal force minus weight of the object, which means centripetal force mass v squared over r minus mg, because weight is given by mg. So this is going to be m 0.5 times velocity 5 squared divided by radius 0.2 minus mass times g. So when you compute this, you shall find yourself having 57.5 newtons. 57.5 newtons. So we continue. Now we are done with that question. Let's check what number 17 is talking about. Number 17 is on a quantity of heat. let's look at it. The quantity of it is a form 3 topic, which is very interesting, and learners are supposed to understand the concepts therein. As we continue learning, let people be reminded of our programs. There is the program here which is running already. You are encouraged to join us if you are in secondary school for physics and mathematics. Learners in Form 1 are studying Form 2 work. Learners in Form 2 are getting introduced to Form 3 work. Learners in Form 3 are getting introduction to Form 4 work. So feel free to join us. Feel free to grow with Shifting Grades Online School. Thank you. Consultation line for the same 0704153366. An electric kettle with a 2.4 kilowatt heating element has a heat capacity of 400 joules per Kelvin. Joules per Kelvin. So that should be capital K. Then we are told water of mass 1 kg at 20 is placed in the kettle. The kettle is switched on and is found that 13 minutes later, the mass of the water in it is 0.5 kg. The mass of water in it is 0.5 kg. Remember, initially, we have 1 kg of water. But at the end of the day, what are we finding? 0.5. Neglecting heat losses and taking specific heat capacity of water as 4200 joules per kilogram per Kelvin. That should be capital K for Kelvin, and for kg should be small letter k. So the constants have not been properly typed, and that one can be understood. Calculate part 1, total heat supplied. We are told that the kettle is switched on and it's found that that is 13 minutes later. So in 13 minutes later, there is a heat given out. So the electrical heat is the electrical energy is being converted to heat energy, and it's usually given by power times time. Power is 2.4 kilowatts, which means 2400. 2400 times time, which is 13 minutes, but now we have to make it SI units by multiplying it by 60. So when you carry out this multiplication, you get 1872,000 joules. That is already correct, but you can still write it as 1.872 times 10 power 6, still joules in standard form. Yeah, that is the total heat supplied. The total heat supplied. Heat used for the kettle. Heat used for the kettle, remember for the kettle, we have the material. We have the material, and it's going to change temperature all the way to 100, because the water in it has to boil and vaporize. So the kettle containing water, together with the water, they are going to change to 100. They are going to change to 100. They're going to change to 100. So from 20 to 100, from 20 to 100, heat used for the kettle, the heat energy will be given by mass, heat capacity multiplied by change in temperature. So heat capacity 400, is it 400? Can confirm. 400 multiplied by change in temperature all the way to 100 from 20, which means we are multiplying this by 80. So it will be 32,000 joules. 32,000 joules. 32,000 joules. It used to raise the temperature of 1 kg of water from 20 to 100. Yeah, very specific. So for water, the quantity of heat will be given by mass, specific heat capacity times change in temperature. So it will be mass 14200 times 100 from 20. This is going to give us, after the computation, 33,600. Then we have Roman 4. We are told also to calculate the heat to change water at 100 to steam. To steam at 100. To steam at 100. So the heat energy which was used there, remember there is a heat energy. There are two things here that I want students to understand, and they are very technical. I want people to understand here that there is an electric kettle here, which is going to release a total heat energy of what has been given here, 1,872,000 joules. When that heat is being used, now part of it will change the temperature of kettle, part of it will change the temperature of water, and the other part is going to convert. The other part is going to convert heat energy. So latent heat of vaporization, that is used to convert. How much is it going to be? So the latent heat of vaporization, latent heat of vaporization of water, the amount of heat which was used there, will be the total energy which was given out minus the one which has gone to raise water and the other one which has been used by the kettle. So that the balance now, the balance from these two is the one which will be used to vaporize the 0.5 kg of water. So this is going to be 1.504 times 10 power 6 joules of energy, times 10 power 6 joules of energy. So this is the amount of heat energy which now was used to vaporize 0.5 to steam, because it was a whole kg of water. It was 1 kg of water, but at the end of the day, the water which had been left now is 0.5, which means 0.5 has been vaporized. So that is the understanding you should be having. That is the understanding you're supposed to have. So a value of specific latent heat of vaporization of water. So we usually say that the latent heat of vaporization is given by mass times specific latent heat of vaporization. So specific latent heat times 0.5 will be the heat which has been used for that. And latent heat of vaporization of water is automatically 3.00 joules per kilogram. Joules per kilogram. Joules per kilogram. Okay. I think we are winding up with this question. State one advantage of using the continuous flow. One advantage is that heat capacity of apparatus is used. In the continuous flow method, heat capacity of apparatus is not involved. Heat capacity of apparatus is not involved. It's not involved. And number 2, there is a vacuum which prevents heat loss by conduction and convection. The vacuum prevents heat loss to the surrounding, of course, by conduction and convection is also minimized. Convection is minimized. Remember, when handling this topic, most of the assumptions that we make are about no heat loss to the surrounding. But no, that assumption is now backed up by some measure to ensure that heat is not being lost. So the vacuum prevents conduction and also convection, ensuring that heat is just flowing from medium to medium. Nevin spilled a little surgical spirit on the back of a ant, and her hand felt very cold. Explain. This is because the surgical spirit absorbed latent heat of vaporization from our hand to evaporate, leaving a cooling effect. Leaving a cooling effect. So the ant is going to feel cold because the spirit is it's highly volatile. It just vaporizes quickly, but for it to do so, it requires latent heat of vaporization for it to evaporate from the body. So it has to absorb it from the body where it has been placed, and that body was Nevin's ant. So the ant will experience a cooling effect. It will be very cold. Define the term latent heat of fusion of a substance. This is the quantity of heat energy required to change. This is the quantity of heat energy required to change a unit mass. Change a unit mass of a substance from solid to liquid at a constant temperature. At a constant temperature. At a constant temperature or without change in temperature. You can use similar words like without change in temperature. Remember, we are winding up now at number 18. Yeah. Now at number 18. A piece of wax weighs 0.27 newtons in air and 0.12 newtons when completely immersed in water. Calculate part 1, its relative density. Now, relative density is usually given by a real weight out of upthrust in water. Out of upthrust in water. So 0.27 divided by 0. Upthrust in water. You know, we have to get the upthrust now. We have to get upthrust. So upthrust is going to be actual weight minus apparent weight. Actually, it weighs 0.27. The actual weight is 0.27. Now the apparent weight, when it is completely immersed in water, 0.12. So 0.15 is the upthrust in water. This will give us 1.8. This is relative density of wax. Relative density being a ratio has no units. Being a ratio has no units. So we can look at number 2 now. We are calculating its apparent weight when completely immersed in liquid of density 0.8. You know, the first thing we are supposed to compute is the upthrust it will experience. The upthrust it shall experience. And how do we get upthrust? Upthrust is given by the weight of the liquid displaced. So we can get its own volume first. Its own volume of wax. Volume of the wax shall be given by, we have its own density with respect to that of water, because the meaning of relative density is density of a substance with respect to the density of water. We say that density mass over volume. So volume is mass over density. So mass over density. So its own mass is 0.027 because the weight is 0.27, then the mass is, when we divide by G, 0.027. Then now we divide it by the density. Because the density of this wax is 1.8 grams per cubic centimeter, then the real weight, the density itself, when converted now, will be 1800. This will be the volume, which means for us to get upthrust, we need the volume times the density. So that will be get mass. Then we have to multiply this by, G. We have to multiply this by G. So if this is the volume of the wax, then it shall displace an equal volume in the given liquid. An equal volume in the given liquid. So we are saying volume multiplied by density times G, 10. Remember 800 is density of the liquid where we are going to immerse it. Density of liquid where we are going to immerse this wax. The wax has a volume of 0.027 over 1800 because its own volume is the one it will displace, but in the liquid now, which have a density of 0.8. Then times G, and this is going to give us exactly 0.12 Newton. This is the upthrust it will experience. And now we wanted the apparent weight. We said upthrust is given by real weight minus apparent weight. So for us to get apparent weight now, then we need the real weight minus upthrust. So the real weight minus upthrust, and this is going to be 0 0.15 Newton. 0.15 Newton. Another question is asking us to explain using the Archimedes principle the upward motion of a hydrogen balloon. Upward motion of hydrogen balloon. So we say that the upthrust due to air, is greater than the weight of the balloon fabric plus the weight of the air inside hence the resultant force moves the balloon upwards. Hence the resultant force moves the balloon upwards. So we are talking of a balloon is here. The balloon is going to displace air. So the air will offer upthrust. Then now we have air inside and also the fabric. The fabric is the material making up the balloon. So we are saying upthrust is the one which is greater now than both weight of air plus the weight of balloon fabric. When you add those two weights, they cannot outweigh the upthrust. And so, according to what we call the resultant vector in physics, now we will say that the motion at the end of the day will be upward. So in Form 4, we talk about floating and sinking together with uniform circular motion as the only topics which appear in physics paper 1. This one is Form 3, quantity of heat. Now this is uniform circular motion, which is Form 4. But up here, yeah, it's the same. It's Form 4, this one, uniform circular motion. But up here, it's linear motion. Now Form 3. Linear motion, Form 3. So talking about machines together with energy, work, power, energy, and machines. Work, power, energy, and machines. Form 3. Up here we have gas laws, the last topic in Form 3 physics. So Form 3. Then at this point, we are talking about Newton's laws of motion, also Form 3. It's good for you to know that physics paper 1 has its backbone in book 3. So revise book 3 widely. It will give you more than 3/4 of the marks in physics paper 1. Thank you so much for following. Invite students to this program. Ensure that they learn with shifting grades. Ensure that they grow with us. Otherwise, we appreciate your support this far. Thank you.